All right, hello everyone. So today we're looking at a Calc 3 problem or multivariable calculus problem. I'm going to find the volume lying inside the sphere x squared plus y squared plus z squared equals 16 between the planes z equals 2 and z equals 2 root 3. Okay, so here's a picture from Desmos just to see what we're looking at, and it'll make our setup easier with our integration. So we have these two planes, z equals 2 lies right here and z equals 2 root 3 right there. And you're basically trying to find the volume that's inside the sphere, the stuff in blue, okay, between those two planes. And just to put things into perspective, the spheres have that cap going on. There's that cap. So, have a point of reference of what we're looking at. So we're going to use a triple integral, and I think the easiest way to do this would be in terms of cylindrical coordinates. You could use spherical as well, however, that would be a little more prolonged process here, because you would have to use, I think, two sets of triple integrals. So we want to avoid that, so we're going to use cylindrical here. And rectangular, that would be a little too much here in terms of just like the actual integration here. All right, so I'm going to turn to this picture right here. And yeah, the amber gold color kind of represents when the plane z equals 2 root 3 intersects the sphere. That's kind of what we saw from the picture at the top. And what you see in red, that's when z equals 2 intersects with the sphere. X squared plus y squared plus z squared is 16. Okay, so we're going to use cylindrical coordinates, and I'm going to, first of all, I'm going to convert our equation that's in rectangular to cylindrical. So x squared plus y squared, that's equal to r squared in cylindrical and also in polar. So we're going to use that. So your equation becomes r squared plus z squared equals 16. Now I'm going to use this equation in so many words to set up our triple integral here. Now, when you're setting up a triple integral, you have whatever method you're using, you would have like 6 orders to choose from. In this case, I'm going to use the order dr, dz, d theta. Typically, most of the time, with a lot of these problems, you do dz, dr, d theta. The issue with dz, dr, d theta, which it can be done, but you're going to run into a problem if you want to go set this up strictly with in that order. So the problem would be this. When you're trying to find your first integral, you have to find what z varies from. So z, for example, if you're looking at this part of the solid, z would vary from 2, right here, all the way to that plane x squared plus y squared plus z squared equals 16. However, over here, the z varies differently. It is from z equals 2 to the plane 2 root 3. So between the two planes, and then out here again, it's between z equals 2 and x squared plus y squared plus z squared equals 16, that sphere. So you have different values for which z varies from. So that's telling you you can't fit that all into one integral. So I'm going to set it up as dr dz d theta, and that would work based on the fact that if you went ahead and remember what r is measured from. R is measured from like the origin to the outward from there. Yeah, your r here would go to 0, and then wherever you're at, your r would always hit the sphere. So r squared would equal 16 minus z squared, and r would equal the square root of 16 minus z squared. Square root of 16 minus z squared. Okay, and I'm going to restrict my values to between plus or minus here. We can technically work with a negative r, but we're not going to get into that. Okay, so if I were to set up my integral, my first integral right here would go from my smallest value for r within that solid, which would be 0, all the way to my largest, which would be 16 minus z squared. Then the next thing that comes along for the right is dz, and z varies here from smallest value of 2 to the largest value of 2 root 3, okay? And then last but not least, theta goes all the way around from 0 to 2 pi. And don't forget you have an r that's in there as well in the integrand whenever you integrate cylindrical coordinates. It's r, and then the d's follow from there. So in this case, dr dz d theta, but you would still have the r if it was dz dr d theta or any combination of thereof. Okay, so that would be my integral. So again, r, you can express that, again, that distance from the origin in terms of z pretty much anywhere in that, within that solid, so that's why we're picking that. Now, if we actually went ahead and integrated this through the power of the iPad here, you would get this answer right here. Not nice, but it is what it is. So 24 root 3 minus 88 over 3, all times pi. The integration itself isn't bad. It's just basically integrating a bunch of polynomials of the sort. Again, just be careful when you're integrating because of the constants and whatnot. But that's how that setup would look like there, okay? All right, well, I hope you find this helpful. Thank you for your time.